My name is Chris Latner, and I'm here to start out the beginning of this talk. So before we get started, I want to talk about where we're coming from, because this is not the first WWDC, and we've been shipping tools for a long time now, of course. And so you can really split the tools that we ship into 4 different categories. If you're on the iPhone, it's very simple. If you build for the 2.0 or the 2.x series of SDKs, you build with GCC 4.0. If you build with the 3.0 series of SDKs, you're building with GCC 4.2. And that's the way it is. There's no choice, nothing to worry about, it just works. 4.2 has a lot of improvements over 4.0, but in particular support for the new iPhone 3GS. On the Mac side of things, it's a little bit more complicated. So as of last WWDC, we supported 3 compilers, GCC 4.0, 4.2, and LLVM GCC. This year, we support the same set of compilers with the addition of Clang. So I'm going to take you through some of the enhancements that we've done to these compilers, and then take you through all the exciting things we're doing. So let's get started. Most of this talk, I should say, is specific to the Mac. The iPhone is, since you have no choice, you get to use the great compilers we have, and you don't have to worry about it. But on the Mac, there's a lot more different options that you have, so we'll talk about that. So the first great feature that I want to talk about before we go any farther is blocks. So yesterday, you heard a lot about Grand Central Dispatch. Grand Central Dispatch is a great API, and blocks are one critical piece that fits into that. But blocks are really not specific to Grand Central Dispatch. If you think about a lot of APIs, they're callback-based. And with a lot of callback-based APIs, you pass pointers to functions around. Well, you pass a pointer to function around until you realize that you have some data that that function needs, and then you end up passing void pointers and function pointers around, right? Well, this really quickly gets nasty and gross. Blocks solve that. A block is also known as a closure or a lambda in other languages. And the great feature they have is that you can write code inline in the middle of another function, and it's an expression. This means you can write your code, and in addition to representing code that can be passed around, you can refer to variables outside of that code. And so here, I have a little block, and this block iterates over all the elements of an array, adding n to it. N is defined outside the block. And the great thing about blocks are the compiler handles the packing of all the data for you. And so you don't have to pass around void stars that you can then cast to structs and all that stuff, right? It just magically is done. So if you use this with Grand Central Dispatch, you end up using it sort of like this. You end up saying, hey, I have a unit of work to do, pass it into dispatch apply, which is the GCD API, and then Grand Central Dispatch handles executing that in parallel on all of your processors for you. Right. So this is a really beautiful natural language extension, and this feature is supported in GCC 4.2, LLVM GCC, and Clang. So there's a whole lot more to say about blocks, of course, and I'm not going to go into it very much in this session, but if you want to find out more, go to the Programming with Blocks and Grand Central Dispatch section, and they'll tell you about it. If you want to, there's also discussion about it in the various Objective-C sessions throughout the conference. So blocks I want to single out because they're the major new feature that we have added to GCC 4.2. If you look at the other enhancements to GCC we've made, GCC 4.0 has only had a small handful of critical bugs fixed over the last year. GCC 4.2 has had 3 features, or three changes. Block support, which we added. It has some bug fixes, and it switched to 64-bit by default. Well, 64-bit by default means that if you run GCC on the command line on a 64-bit machine, it will default to producing a 64-bit binary. But if you're using Xcode or you're passing the -arch series of flags, you won't see any change. Aside from that, GCC hasn't really changed. So if it's okay with you guys, I'd spend the rest of the time talking about LLVM and Clang. Is that okay? So let's dive in. So a quick recap. What is LLVM? LLVM is really about a new strategy for compilers, right? We've been using GCC for many years. We all know it. It works, but it's just not great. So we're shipping compilers based on LLVM. These compilers are available along with GCC, so you can use them if you want to, but GCC is still there. A great thing about it is that LLVM is open source, and so you can actually join in the development that we do with LLVM at the website. We have mailing lists, bug trackers, all that kind of stuff there. You saw the cool new LLVM logo that we whipped up for the conference. So the dragon comes back to The dragon implies like Dragon Book and compilers and all that stuff that fits together. In case you're wondering. So that's what LLVM is. So why not just fix GCC, right? Well, the real answer is that GCC doesn't really, it's not a strong platform for the things we want to do in the future, right? GCC is a compiler, it does what it does, but getting it to do anything that it wasn't originally designed to do 20 years ago is really hard. And so LLVM is really the answer for that. We want to do something new, we want to push forward. I think there's a huge amount of innovation that we can bring to compilers, and we're just starting to do that now. So LLVM is all about redesigning how we build compilers. We build them as libraries. We build them as libraries so that we can use them in new ways in different applications. So we can reuse them. So we can use, an x86 code generator in some way that, we never would have thought about when we built it in the first place. So we're focusing on building something that's fast, flexible, performant, supports all these crazy features. In case you haven't noticed, GCC has a lot of features. And so making all that happen has taken some time, but I'm really happy to say that we're to that point now. And so now that all of that work has been done, we can start building on doing new exciting things with it. So, of course, LLVM, as we talked about yesterday, is not just used in traditional compilers. OpenGL, OpenCL, and excitingly, the static analyzer built into Xcode are really great demonstrations of what you can do with compiler technology that most compiler people don't think about, right? The static analyzer is a great example of how the compiler's data flow analysis can really be used to solve interesting problems that aren't related to just making code go faster, which is really exciting, but very different. We also have LLVM GC in the client compiler. So to tell you about some of these applications, I'd like to bring Evan Chang up on stage, and he'll tell you about what we're doing with LLVM here at Apple.
Thank you, Chris. Good afternoon. My name is Evan Chen. I work here at Apple's compiler team. So here at Apple, we've been doing a lot of very exciting things with LLVM. I just want to go through a few of them today. I hope you enjoy it. First, you've heard Chris talk about LLVM, GCC, LLVM GCC, CLAN. You might be wondering, what are these things? What exactly is GCC? How are they related? So LLVM is a set of libraries, a philosophy, it's a dragon, it's many things. So how does it fit? Well, if you look at a static compiler like GCC, you can roughly break it down into 3 parts, right? You have the front end that's responsible for parsing your program. Then you have the optimizer that transforms your program to make it go fast. Then the code generator translate that into the machine language. Well, think of LLVM GCC as taking the GCC front-end technology and replace it, the optimizer and code generator with a kind of a turbocharged engine, the LLVM optimizer and code generator. And looks, smells, tastes just like GCC, but it's better. And we want to with CLAN, we're taking a step further by replacing the front end as well. Just completely do away with the GCC technology to produce and kind of stitch the CLAN front end with the LLVM optimizer and code generator to produce a CLAN compiler. It's very exciting, and Chris is going to talk to you all about CLAN later. But for now, let's focus on LLVM. So again, LLVM, if you take a look at LLVM GCC, it's just a traditional static compiler. One of the major things with a static compiler, one of the common things with static compiler is depending on other tools to kind of take the code that's generated by the compiler and produce an executable. So for example, LLVM and LLVM GCC and GCC both produce assembly code, and then requires assembler and linker to kind of produce executable. Well, there are other compilers out there, right? Compilers that are embedded in applications, in the OS, in many other ways that they compile code on at the runtime. We call these just-in-time compilers or dynamic compilers. So these are not new. The new things with LLVM is we take the same optimizer and code generator, and we produce static compiler, but we can also use it to produce just-in-time compiler. So here at Apple, we use this reusable components of LLVM, or we call the LLVM backend, to produce a number of different applications, different JITs embedded in as part of OpenGL and OpenCL. Let's take a quick look at them. First, OpenGL. You know OpenGL? This is a language for you to program your GPU to do 2D and 3D graphics animation. Well, OpenGL is a very big standard. It has many, many features. Not every graphic card supports all the features that's in OpenGL. When that happens, the OpenGL system will take the function you request and basically dynamically compile the code into code that's executed on your host CPU. There are a couple ways to kind of support this, right? The older implementation use custom JIT and interpreter to support this. The problem with custom JIT is for every different architecture, you have to have a different custom JIT for it. Well, the problem with this is obvious, the higher engineering and maintenance cost. And furthermore, as OpenGL evolves, you need to add new features. You require to have putting more optimizations to support these new features. That's not that easy to do with a custom JIT framework. So one of the ways to deal with this problem, we can fall back into an interpreter that supports all the features, runs on all the platforms. The problem with the interpreter is it can be over 100 times slower in some cases. So we have replaced OpenGL implementation with one that's based on LLVM. The great things with LLVM's code generator is it can target a variety of different architectures. And there's a single optimizer, single code gen that supports everything. And it's because it's a general compilation framework, it's really, really easy to put in new optimizations, support the new functions that's in OpenGL. So the result is a more rigid, a more flexible framework, OpenGL implementation. And the ones we have learned that turn out to be faster than the older implementation. The next example is OpenCL. OpenCL is this new technology in Snow Leopard you've heard a lot about. Well, if you boil it down to it's a new way for you to write C programs to tap in the computation power, not only on your CPUs, but on your GPU as well. This is a very powerful way of programming. Of course, to support this, you need a number of kind of interesting technologies. You need a C parser that's fast and a small memory footprint that can embed into the OpenCL system. You also need a backend compiler that is capable of targeting not only your CPUs, but your GPU as well. Of course, it's no surprise. OpenCL is built on top of the Clang frontend and LLVM backend technology. And not only that, the whole point of OpenCL is speed. You want to run your program fast. So the compiler must produce great code and must compile really, really fast. Well, in Snow Leopard, we have replaced the core image implementation from a custom JIT, a very well-tuned custom JIT implementation, to one that's built on top of OpenCL. And the result is 25% speed up. That shows how powerful the OpenCL is and how powerful the LLVM technology is. If you're interested in learning more about OpenCL, I encourage you to go to the Introduction to OpenCL talk on Thursday. So LLVM is a very exciting compilation technology. It's very powerful. For you developers, you want to take advantage of it by compiling your code with Clang or LLVM GCC. For the next part of the talk, we're going to focus a little bit more on LLVM GCC. Why is it a worthy upgrade from GCC? When we design LLVM GCC, we have a number of goals in mind. Well, we want it to be a drop-in replacement for GCC. If you're compiling your code with GCC, you should be able to migrate to LLVM GCC by selecting a different compiler. There's nothing else you need to do. So the first thing we want to support is 100% source and binary compatibility with GCC. And of course, there's a lot of GCC features you can't rely upon. LLVM support LLVM GCC support all the major features that GCC provides. And of course, this is built on top of LLVM, so you expect it to be fast, compile code fast, and generate fast code. So last year WWDC, we introduced LLVM GCC as one of the compilers. That was a great release of LVM GCC. It supports majority of the GCC features, but we left a few things out. But this year, we added support for stack canaries, obviously new blocks feature, OpenMP, and we really improved debugging support. So this year, we're very happy to say LVM GCC now support all the major features of GCC. Thank you. Next, let's turn to the things that make us compiler geeks really excited. Speed. So speed is two parts, right? Compile time performance as well as speed of the generated code. So we have a different philosophy here. Because LVM is going to be part of the runtime system, it's built to be a JIT and part of the operating system, compile time speed is very, very important to us. So we really work very, very hard in this area. We want to compare LVM GCC against GCC. Well, the example I'm going to show you is AppKit, which is a very, very large Objective-C framework. And it's thousands and thousands of source files. We found this is only one example, but the results are pretty representative of everything we've tried on. Let's look at compile time. So we're going to look at both release mode and debug mode. In release mode, the default compilation option is -OS. That means optimize for size, but not at the expense of speed. This turns on most optimizations. In debug mode, it's -O0-G. That turns off just about all the optimizations done and codegen really, really fast. So as you can expect, debug mode compiles really, really fast compared to release mode. Let's see how LVM GCC does. Well, in release mode, LVM GCC is 1.5 times faster, 35% faster than GCC. What does that mean to you? Well, I'm sorry to say we have shortened your coffee break by roughly 8.5 minutes here. So, but your productivity has just gone through the roof. Well, and how about debugging? How about debug build? Well, last year when we released LVM GCC, we noticed LVM GCC is doing way too much work at O0. We still try to optimize your code even though you don't care about it. So it turns out LVM GCC was slower than GCC last year. Well, this year we're putting a lot of work. We've caught up and surpassed GCC by a bit. So you might be wondering why it's only 5% difference. Notice with optimization turned off, majority of compile time is in the front end, parsing time. Since we share the same front end technology as GCC, there's not a whole lot we can do here. Of course, that's an excuse, and we don't want to use that excuse. We want to do a lot better. We'll talk about that later in the talk. So LVM compile code faster. Does it compile code generate better code than GCC? We want to do the comparison across a number of benchmarks and focus on Intel performance, both 32-bit and 64-bit. Let's see how we do. You have seen a lot of numbers in the DT's State Union talk. For this talk, we're going to focus on a smaller set of benchmarks. First, let's take a look at OpenSSL. OpenSSL, as you know, is a kind of open source cryptography library that a lot of applications are dependent upon. The data points here are different ciphers, different message digest systems. They all behave differently, have different reaction to compiler changes. So the speed up here, as you can tell, is across the board, right? Some cases, we do slightly better than GCC, 4%, 5%, but there are cases where we're over 20%, 30%, or over twice as fast than GCC. Think about what that means to your application. That means a secure transfer goes much, much quicker. Thank you. In 64 bits, the difference is not quite as dramatic, but again, most cases we win, LVM GCC wins. The difference could be small or could be over 20% faster. So at this point, you may be wondering, is there a way I can tell LVM GCC to work really, really hard? You know, just give me the best you can do, forget about everything else. The answer is yes. LLVM GCC provides you with a link time optimization feature. What does link time optimization do? Why can it squeeze more performance out of your program? Well, link time optimization is a way for LLVM to optimize your code by working across all the files at the same time. So traditionally, when you compile one source file at a time. The best the compiler can do is look at all the functions in that single source file. With link time optimization, you still compile one file at a time, but the linker at link time is going to take all the source code and it's going to call back to the LLVM optimizer and code generator. So it's going to work on your complete set of source files at one time. It's going to do aggressive inter-procedure optimization. For example, it can inline one function in one source file into another function in a different source file. It can do all kinds of very aggressive optimization. What does that mean? It means it sometimes can squeeze out performance that even the programmer may not be able to do because it could work on such a big scope. Well, let's see what LTO can do. Take a look at the OpenSSL example. Here, we're looking at 2 data points. In one case, LLVM GCC already does quite well. It's 20% faster. In another case, it's behind GCC by 1%. With link time optimization turned on, the first case got even faster, 5 additional %. The second case got 10% faster. It turns a slight loss into a win. Thank you. Here's another case, JPEG decoding. JPEG is such a well-known compression standard. The decoder has been worked on over the years. It's been tuned and tuned and tuned. There's really not a lot of room for improvement. In fact, LLVM GCC does okay. It gives you 1% of performance benefit. Not interesting. With link time optimization, we're able to squeeze out 7% additional improvements. And link time optimization is very powerful. It's also extremely easy to use. Without implementation of link time optimization, all you have to do is go into Xcode, change the configuration, compile configuration, and select link time optimization. If your project is makefile-based, it's also really easy. Just add the -f LTO compile time option. Alternatively, you can use -04, which is equivalent to -03 and -f LTO. So we know LLVM GCC is a great compiler. It's relatively young, but it's also very mature. It's a production compiler. In the Snow Leopard you got, we're already building several bits of the Snow Leopard with LLVM GCC. Core data, of course, OpenSSL, but also Java Hotspot. I'm pointing out Java Hotspot because it's such a huge cross-platform project. It's millions of lines of C++ code. Use every trick in the book to get performance. If LLVM GCC can compile Java Hotspot, it can probably compile your C++ project. So to recap, how does LLVM GCC compare to GCC 4.2? Well, we got all the features that GCC provides, and we'll also give you link time optimization. And LLVM GCC generate better code than GCC. And LLVM also is significantly faster in terms of compile time in release mode. In debug mode, we're only slightly better. So we need to rethink the problem. We need a new front-end technology, new parsing technology that's significantly faster. That's where Clang comes in. I'd like to ask Chris to talk to you about Clang.
A new front-end technology. Why would we do that? I mean, C's been around for years. How could you possibly improve a C compiler, right? Well, it turns out there's a few ways. So what is Clang? You've heard about this a few times already. It seems like we like to overload terms here. So LLVM means about 4 different things, depending on what context you're asking. Clang also means several different things, depending on who's asking and what they're asking about. The first, Clang is a set of libraries, right? A set of libraries built just like LLVM is. And so right now, this implements a C and Objective-C front end and it follows the normal LLVM design approach. So we go for modularity, reusability, and this is what allows us to build the static analyzer, right, which uses the front end but not the code generator of LLVM. Clang is also a compiler, so you can pick it out of Xcode and use it to build your apps. And this combines the strengths of the Clang front end with the power of the LLVM backend and optimizer. Finally, Clang is also an open source project. Clang has a much better web page than LLVM does, and you can find it on clang.llvm.org. So why do we care, right? Well, the great thing about being a compiler person is that people make fun of you, and oh wait, no, that's not the right thing. The great thing about being a compiler person is that you can build tools that you use yourself, right? And this is the same for all of developer tools, right? We build tools because we're programmers. And we want programming to be fun. We do this all the time. Let's make it great. And so that's why we care about things like fast compile times, fast generated code, and great features. Right? So Clang and LLVM going forward are really where we're investing in this. We think we can make things a lot better than they are now. We can push forward, and there's a lot of work to be done. So I'm going to do the first ever compiler demo that I know of, just to give you an idea of what this feels like. So here I have a simple Objective-C app called Blast App. This is a developer example that we've shipped before, and you can download it from the web page. And like many applications, this builds with GCC. And so if we build this guy with GCC, you can see how this works. Let's just make sure it's all clean. And we hit build, and you can see 1, 2, 3, 4, 5, 6, roughly 6 seconds to build this app. Well, switching to either LLVM, GCC, or Clang is really easy. You just go to either your target or your project settings in Xcode, and you say Edit Active Target. You get a nice list of different options, and you can search for compiler. And then one of the options here is the compiler that we're using, right? And so here's GCC. And so if you pick this guy, you can pick a number of different options. You can pick Clang, you can pick LLVM, GCC, and they all work really well. One nice thing about picking Clang out of Xcode is if you have a mixed project that has C, C++, Objective-C++, all mixed together in the same project, that the C and Objective-C pieces will build with Clang, and the C++ and Objective-C++ pieces will build with LLVM GCC. So it's completely transparent. So now that we pick that, we're done. All we have to do is hit build, and you see 1, 2, 3. Whoa, okay. Well, So the reason I like to do this is not because it is, a specific % faster than GCC. That's really not the point. I mean, I'll show you numbers later, but the point is that Clang feels a lot faster. It's not just one of these theoretical numbers that you throw up on a chart. Just doing development with Clang, it's a much nicer experience, and I hope you agree. So if we come back to slides and keep going. So I gave you a brief introduction to what Clang is. I want to talk about several different topics related to Clang. Compatibility, specifically GCC compatibility. This is the limiting factor of whether or not it will actually work with your code. Talk about compile times. Give you some more detailed numbers than you saw yesterday. Talk about some nice features that Clang has, and I think that you'll like some of these, and then we'll wrap things up in the end. So the first thing that we want to talk about when it comes to compatibility is C++. Well, I know that many of you are thinking, oh, well, Clang only supports C and Objective-C, and I use C++ for everything, or a big chunk of my stuff, and therefore Clang is irrelevant. Well, obviously, C++ is a critical language for us. It's a critical language for Apple, it's a critical language for our developers, and I'm happy to say that we're committed to implementing this. It's a ridiculously huge language, but we're going to do it. Beyond just doing it, we actually intend to do a really good job, because one interesting factoid is that Clang itself and LLVM itself is all written in C++. And so we have some motivation to do this. I've also noticed that C++ compilers seem to have some room for improvement too. So maybe we'll be able to do some good things there. So that said, Clang currently has no C++ support, as we said before. And so if you try to build an Xcode project using C++, it'll use LLVM G++ for you, and your program will build just fine. You just won't get the benefits of Clang on the C++ code. So I'm happy to say that not only are we committed to doing it in some abstract theoretical way, we've actually been working like crazy on this, right? C++ is a big enough feature that you want to start early because it takes time to do. And not only are we to the point where we can do things like, references and, bool and, really exciting features like that, we're to the point where last week we started implementing things like partial template specialization and other features that are actually, real C++ things. The caveat being that C++ is a huge language and there's still a lot to be done. So if you're interested in learning more, we have a lot of details about C++ progress on the webpage, and patches welcome. So command line compatibility. So continuing in our theme of compatibility, one of the big things we want to make sure that you could do is take Clang and drop it in and build your code with it, right? And so because of this, we've worked really hard to make Clang as compatible as possible with GCC, even on the command line. And so this means that all your favorite or most hated command line options for GCC should work just fine. This means that if you have a makefile, you can just set cc equals to Clang, and it's in the developer user bin folder in most installations, and it should just build just fine. If you do this, you don't get the auto fallback to LVMG++, and so usually you can set CXX and your makefile will do the right thing, right? But it should be really easy to use. The next thing is source compatibility. So who here loves it when you upgrade your compiler and then it says, oh, you have an error that you didn't have before? Is that your favorite feature of compilers? Yeah. I'm not seeing a lot of hands here. Yeah, I've noticed that too. And in fact, any difference between compilers really prevents it from being adopted, right? Because if you upgrade compilers and say, oh, I have 10,000 errors, well, is it really worth it, right? That's going to take a lot of time to adapt to change your code. Well, I'm really happy to say that we put a ridiculous amount of work in making Clang compatible with GCC. So not only do we support the C standard, we also support a bunch of GCC extensions. So things like inline assembly is an obvious one that many people use. We support a broad range of GCC extensions. We also support a broad range of interesting quirks, that are dubious, and then even some outright bugs that GCC has that real code depends on. And we're committed to doing things right, and so if we have a bug or a quirk that you're depending on, we'll output a warning where GCC wouldn't. The nice thing about that is that then you can decide whether or not you care about it, and you can deal with it at your leisure, right? But this means that you can basically just pick up Clang, use it, and it should work, which is very powerful. That said, Clang still is a relatively new technology, and when Clang builds your code, you should have confidence that it does work. But if you use a feature that we haven't implemented yet, you'll get an error from Clang. And so if you use OpenMP, for example, Clang doesn't support that yet, so your program, in the case of OpenMP, just won't be parallel. If you use nested functions or the crazy underbar label thing or a couple of other similar levels of obscurity features to GCC, Clang will output an error and say, hey, I can't build this. For right now, that means you have to build your code with LLVM GCC. Sorry. That said, we've run a ton of code through it, and so we're pretty confident that the major bases are covered. So Objective-C is very similar. So we also want to be extremely compatible with Objective-C. The only difference here is that there are a few things that we intentionally decided to remove from Clang. And these are things that are either wildly incorrect that we discovered in a new implementation of the language, or some things that were already deprecated in GCC. And I'll give you an example of these, and I hope you agree they're pretty gross. So if you depend on these, you're going to get an error message out of Clang, and it should say, this is invalid, and we don't plan to add it. And so if you use these, you should fix your code. And there's two reasons to do this. One, we're moving to Clang, and so you need to eventually get your code to build. A second big reason is that the static analyzer uses the same parser as Clang, right? Or it uses the Clang parser. And so it won't work on your code either. And so fortunately, these are pretty weird things. Cast of supers is one example of that. So cast of super, the instances I've seen have occurred when people were passing around instance variables and they changed it to call super instead, and a cast remained. Well, in Objective-C, super, and this sends a message to your superclass. Super is not supposed to be an expression. It's supposed to be a magic token in there. And so we fix this, and usually it's just a matter of removing that cast from your code. Cast of L value is another interesting example. Cast of L value is a crazy GCC feature that even they removed from their compiler. But we had it accidentally enabled for Objective-C, and so some of these guys snuck into some Objective-C code bases. So this was outputting a warning already with GCC, so hopefully you've already fixed this. Generally, instead of assigning into a cast, you cast the thing that you want to assign, and it's a much better way to go. The third one's really interesting. So this is 64-bit specific, and in 64-bit, 64-bit Objective-C uses what's called the non-fragile ABI. This allows, at link time, you to add instance variables to your classes. Well, that means that the size of an interface is only specified at runtime. It's not specified at compile time. And GCC lets you use sizeof. Well, what does sizeof give you? It gives you the size of the class when GCC saw it. And that's not the same size as when you run your app, which is a pretty scary situation. The fix for this is really easy. You just change your code to call the Objective-C runtime function class get instance size. And that's all you have to do. So I hope you agree these are some pretty weird and pretty corner case things. Most Objective-C code just builds just fine the first time. If you try Clang and you have any problems, you're welcome to come to the lab tomorrow morning, and a fleet of compiler engineers will be happy to help you with your code. So the last thing I want to say about compatibility is a gotcha. So the trajectory of C has followed a couple of different steps. Before 1989, there was no standard in C. It was this weird soup of different implementations, and nobody's compilers agreed. In 1989, the language was standardized in the ANSI and then the ISO language standards, and that gave us C89. 10 years later, they had a new language standard called C99. C99 adds a whole bunch of features to C. Well, GCC has always defaulted to C89. And so now I'm happy to say that Clang is going to leap into the future and default to a language that's only 1 decade old, not 2. So C99 is pretty much a transparent extension to C89. There's only one minor thing, and that's inline. So if you build your app with Clang and you specifically say the compiler should use its default compiler and you get some link errors, you may find out that those are inline functions. And so inline changed between C89 and C99. The easy solution for this is just change inline to static inline, and it will work in both modes. It will work with GCC, it works with Clang, everything is good. The other fix for this is you can explicitly say, hey, I want C89, and you can do that either in Xcode with the C language dialect setting, or you can say -std equals C89 or GNU89 on the command line. It's really easy. And so if you don't tell Clang a language to use, for C it'll pick C99. Should be pretty straightforward. So those are the only compatibility gotchas that we really have to talk about. So we've built it to be extremely compatible with GCC. You should be able to drop it in and it just works. If you're using a feature that Clang doesn't support, it should tell you. And if you're using something crazy that we intentionally removed, it should tell you that. And there's a C99 thing. So it should be really, really straightforward to adopt. So compile time speed. Well, so this one's interesting. Yesterday, Andreas told you that Clang compiles code twice as fast as GCC. That's true, but it's only part of the story. If you look at how much faster Clang is than GCC, it's a lot more interesting. So here we have a whole bunch of different applications. The ones on the left are a bunch of Apple applications like Mail and Automator and Dashcode and even Xcode. These guys are a couple open source applications, and these are some developer examples that we've shipped, just for a range of different source code. And if you look at how much faster how much faster the Clang compiler is than the GCC compiler, it's actually pretty fast, right? So I'll talk about why this is later, but you can see that in almost all cases, results vary, of course, but in almost all cases, Clang is almost 3 times as fast as GCC. That's a pretty big victory right there. And, well, it's not an accident, of course. This is because we've fought really hard to make it happen. But this is also in a debug configuration. So this is in the configuration where you're almost completely front-end bound, right? So this means your O0 compiles, which is where we all do our development in, should be a lot faster, right? So, but the compiler speed is only part of the story. And so the compiler, being fast, is good, but when you do a build, you do a lot of other things. You run the build system, you compile some nib files, you copy files around, maybe you have some custom build scripts and other stuff in your project. And so if you look at total build time, there we see it's about twice as fast. And so Clang is about twice as fast when you include all the other stuff that we haven't sped up. And so this is what you see when you do actually build from Xcode like I did before. So that's great, because this is what you care about, right? An interesting note here is that there are things you can do that go wrong, right? So Dashcode, the interesting reason that it's a little bit slower is it uses a custom build step that uses a Java app to do some compression or something like that. I'm not familiar with all the details, but if you do custom build steps, of course, the compiler can't help you. So I think those are some amazing results, and the question is how do we do it? Well, there's not one easy answer, right? I mean, it's not like we fixed one problem in GCC and it magically got dramatically faster. If you boil it down, there's thousands of specific engineering decisions we made, or the specific design decisions we made to achieve this. We can wave our hands and say it's better algorithms and less memory, but I want to give you an example of two things. One is this LLVM and Clang separation. So GCC, when it was implemented 20, 25 years ago, was built as a C compiler, for VAX or something, where they brought up the code generator and they brought up the C front at the same time. And because they did this, they got intertwined a little bit because it was easier. Well, over time and over the next 20 years, it got even worse. And so it's this big intertangled mess. Well, the problem with that is that GCC spends a lot of time and even more memory on doing things that don't matter. So specifically, if you look at like a structure declaration, GCC saves space memory in a structure declaration for back-end code generator stuff, right? Well, in our system, we have huge headers with millions, or well, not millions, thousands of structure declarations and enum constants and all this stuff, right? Well, any one .m file doesn't use most of those. And so if you spend memory on that, you're just wasting it, right? Because the code generator doesn't code gen stuff that you're not using. LLVM and Clang are very different. I mean, I think you'll believe me that LLVM doesn't depend on Clang because we've been using it for a long time before Clang even existed. But we've intentionally built Clang to be separate from LLVM as well. This is to allow things like the static analyzer and other things that don't use the code generator, right? Well, the good thing about this is that keeping them separate and unentangled really helps us both in purity and reusability and all that stuff, but also means that we spend time and memory doing things that really matter. We only spend memory on stuff that, for the code generator, actually goes through the code generator. This is not that novel of a concept, but it's actually a pretty big design decision in GCC that would be almost impossible to reverse, right? And so this is an example of design and how it impacts performance and memory use and all that kind of stuff. Another thing I want to talk about is precompiled headers. Precompiled headers are what we use on the system to handle the fact that you have 10 megabytes of headers coming into your 100-line .m file, right? And so if you're not careful, you spend all of your time parsing these header files, right? So if we look at PCH, we can look at how GCC does it and how Clang does it. Well, there's two scenarios, generation and use. And you can see that here we're looking at memory use. GCC takes almost 125 megabytes to generate a PCH file for, say, cocoa.h. But it only takes 48 megabytes of memory when you use it. Well, that's good because you only generate it once and then you use it a lot of times, right? Well, we've finally optimized our PCH implementation to be dramatically lazier. So instead of pulling in everything off the disk, we only pull in the declarations and the types you're using as you compile a file. Because of this, Clang uses substantially less memory. When we generate the PCH file, this is head-to-head engineering difference, right? Because of things like we talked about before. And so you can see that just by engineering it differently better, it's twice as good. But by making it dramatically more lazy, we got a 4x reduction in memory use. Well, this can really impact your build, right? If you have a laptop that doesn't have very much memory, it's quite possible you're going to be swapping with GCC. Well, going from a scenario when you're swapping to not swapping is more than 2x speed difference, right? And this can be a huge difference in your build performance. Well, beyond just being faster or using less memory, PCH files are also dramatically smaller, right? And so if you're using network builds or other things where you're shipping PCH files around, this can be a huge impact. And so we've really put a lot of work into finally optimizing specific pieces of Clang that are used and are really important in our scenarios, right? And the problem is that with GCC, the GCC folks really care about building Unix apps. And Unix apps typically are C files with a 10,000-line header file, right? That's not the way our system works. And so we're not getting a lot of support from the community to help improve GCC in this respect. And at the end of the day, the design would be very difficult to fix anyways. And so that's why we can push Clang forward and we can do the right things for our system. And the results, I think, speak for themselves. So I've told you all about how we want to be exactly like GCC, but faster, right? Well, I have a hard time being limited to doing exactly what GCC does because GCC really isn't that great at a lot of things. So can we do anything better than GCC? The answer is yes, right? So I want to talk about error and warning improvements. Andreas talked a little bit about this yesterday, but I want to give you some more examples, right? Errors and warnings, what we call diagnostics, are really important. It's not some glitzy feature, but errors and warnings are things we deal with all the time. If you can make me be 30% faster at getting to the problem and fixing it, then that's multiplied by 100,000 bugs that I introduce in my own programs, and that makes me a lot more productive, right? So we put a lot of time into this, and this is something that really matters. And the problem, of course, is that GCC is just really not great at this. Here's a typical example. So here I have some apparently perfectly legal code, and I compile this, and I get this very insightful message from GCC, right? Yeah. So I've gotten to the point, basically, when I'm using GCC, I don't even read the messages anymore. I just find the line number, and I go scrutinize the line and try to figure out what I did wrong, right? That's how bad it is. Well, with Clang, we want to push this much further, and we want to do a lot better. And so, of course, I'm happy to say we are, right? So here's an example, same example, and the difference between what GCC tells you and what Clang does, right? Here, Clang will tell you, hey, I don't know what NSString is. Well, obviously, I forgot to include coco.h, right? Well, that message doesn't tell me anything about what the compiler's thinking. And it is legitimately a hard problem, and it takes a lot of work because the compiler just knows something's wrong. It has to guess or infer what you did wrong and tell it to be able to explain it in a way you understand. But this is a problem that's worth solving, and so we've put a lot of effort into it. And this isn't just for Xcode. If you run Clang on the command line, you can also see very nice-looking output. In this case, we actually print the error and the line of code that it occurs on to the command line, which is really nice when you're doing command line development. Another example is range information. So here's a great example from yesterday where we have 4 pluses on the line and GCC tells us something's invalid, right? Well, in Xcode, it's beautiful. You get these awesome highlights of the sub-expressions for these kinds of things, and it says, hey, this sub-expression is the problem. This is really useful when you have things that are like precedence issues and things like that. This is also really nice for saying, hey, this is supposed to match that, and the compiler can highlight those and say what's happening. The same thing also happens on the command line. We underline the various pieces, and we only print out one line, so it's not quite as nice as Xcode, but if you have errors that are spanning thousands of lines anyways, then hopefully you can fix it without that. But these are just 2 examples, right? I want to tell you a couple more cute things. Let's look at macros. So macros are really interesting because often you don't know something is a macro. Here I'm just calling max, right? And I included the definition of max just so you could see it. But I get some error message from the compiler saying, hey, I have invalid operands, right? Which is the generic message saying there's something wrong. I didn't write a greater than. I don't even know that's a macro, and I'm getting something from the compiler that doesn't make any sense to me, right? Well, with Clang, it's really nice because the front end has been designed to keep track of this information. Not only does Clang tell you that you have that error, it actually unwinds all the macro instantiations that are involved in that, and it tells you the different levels and highlights it. And so here you can say, that is the greater than, that's the problem, and here's where it came from. In Xcode, in the build results window, you can click on the instantiated from line there, and it will jump right to the macro definition so you can look at it. It's really powerful and really, really nice. But that's not all. So there's a lot of other things we've put, a lot of other improvements we put into this. How about warnings? You get a warning out of your compiler. The compiler inevitably has some flag that controls that warning, but how do you figure out what it is? Well, Clang tells you. It says, hey, here's a warning. If you don't want this warning, that's the flag that controls it. And I'll talk more about controlling warnings later. It's a very simple thing, right? If you design it in so that you have a database of warnings, right? Well, one more example. So this is a little picky, but this is the kind of thing that has always irritated us, which is, here I've forgotten a semicolon, and GCC tells me that it's on the curly brace line. Well, that's not where you put a semicolon. What is it talking about, right? I mean, Clang will actually tell you you're supposed to put it there. If you click on this in Xcode or you click on the build results window, it will actually go to the right place so you can hit the semicolon instead of going to the wrong line, right? I mean, this is little details like this, but this kind of stuff adds up over time. And coming back to C++, a lot of the improvements we've made for Clang for diagnostics are important and useful in C, but I think that C++ are really where a lot of it will pay off. So C++ has things like typedefs, right? Well, Clang is very good at preserving typedef information. The idea being that if you get an error about std string, you get an error about std string instead of std basic string, all that kind of stuff, right? And so we put a lot of effort into making this great. And I think that you'll like it. You should play with it. Talking about warnings, warnings are really interesting, right? Because there's a lot of ways that you can control them. So you can control them with the -w foo flag for the foo warning, right? And you can also turn it off with w no foo. You can also turn it into an error with -w error equals foo. But one of the things that I've talked to, and maybe I hang out with some very pedantic people, but a lot of people like building with w error, right? If you build with w error, you get one warning, you're dead. How do I get rid of it? Maybe I can't change my code, right? Well, I'm happy to say that you can actually turn off specific warnings. You can even turn specific warnings back into warnings in w-error mode. And so if you build with w-error, but -w no error equals foo, this says, I want all my warnings to be errors except for that one right there. And you can either make it a warning or you can make it just completely ignored, right? And so this is really nice. This lets you do things. But there's a little bit more, right? Because this lets you can control on a profile basis. Wouldn't it be nice if you could actually have a little bit more control over this? Well, something that people have suggested to us for years, but it's very difficult to pull off, is controlling warnings within the file, right? I have a specific warning I want to get rid of. Stop it now. Well, with Clang, you can use a simple pragma to control this. You can say, ignore this warning at this point, or turn it into an error at this point, right? This is really great if you have something like Bison producing a C file, and Bison injects all this code that does all these horrible things and produces warnings. I love Bison. Bison's great. But I mean, you can use this for a lot of different things. Combine this with the fact that Clang tells you what warning flags control various warnings, and suddenly you have full control over what's happening in your compiler. Amazing, right? So we put a lot of effort in making this really nice and really powerful. One other nice thing about using pragmas is that you can use this in your code, and GCC will just silently ignore them. And so you don't have to do if-defs or any other weird things. This is just, you can use this in your code, and there's no problem with that. Let's talk about something else. So we explained that OpenCL uses vectors, or OpenCL uses Clang, right? And OpenCL is all about performance, and one thing that's really important for performance is vectors. Well, Clang has a lot of really nice vector extensions that you can use directly in your code, even if you're building applications, you're not using OpenCL. So here I show you the kind of gross, horrible syntax for defining a vector type. With this definition, I get a new float 4. And this says I have a vector of 4 floats. With this, I can now declare some vectors. Now, GCC has a vector extension that's similar to this. They call it the generic vector extension. Clang also supports that extension. But while you can declare vectors and you can do basic operations with the GCC vectors, you can do things like loading them, storing them, multiplying them element-wise, adding them, stuff like that. There's no way to get to the elements of the vector. If you want to get element 4, you have to make it a union with an array and then use the array to get the element of that vector. That's horrible. I mean, the whole reason you're doing this is for performance, right? Now you're going to memory? Why are we doing this? I mean, that's bad. Well, Clang has a lot of really nice syntax for doing this. If you want to get to element 3 of your vector, you use subscript 3. This is where you gasp. This is amazing technology. It also has a number of nice things from OpenCL, like access to all the even or the odd elements of a vector. If you're doing things with complex numbers, for example, this is a really nice way to extract out all the real or the imaginary components. It also supports GLSL-style swizzling operations. So you can say v.xxxxx to get a splat of all the x elements. We even have a built-in that you can use to do a fully general permutation of any 2 vectors. In this case, I'm taking 1 element out of v1 and 3 elements out of v2 and doing my own custom mix. right? And because this uses the LLVM backend, you can be sure you're getting really good code out of that. And this is how OpenCL works, and it's a very powerful set of extensions. It lets you write really portable and really powerful code. So if you want to learn more about the syntax, the Introduction to OpenCL session can tell you all about this. I only have one slide on it. So the question now is, can I actually use Clang, right? So I've told you, hopefully, why Clang is really cool, why you should want to use it. So now, can you actually, in fact, use it? Well, I'm happy to say that yes, in fact, actually, Clang does actually work. It might be hard to believe. So we've been working on Clang for a long time now, 2.5, 3 years, something like that. And Clang, remember, is building on the LLVM code generator and optimizer, so it's using the exact same well-tested optimization and code generation technology LLVM GCC is using. And as I told you before, if it sees something it doesn't understand, it doesn't hope for the best and keep going and output code and it might work. It actually says, no, I do not understand this. Sorry, right? Well, beyond design philosophies and principles, we've also done a huge amount of testing. And Clang, again, is an open source project. We've had a huge input from open source people building little apps, right? Little apps like, the FreeBSD kernel. And FreeBSD user space. And at Apple, we've done a huge amount of testing on internal apps. I mean, you saw a big list of apps up above. So we've done a huge amount of testing on this. And the FreeBSD kernel, of course, not only builds, it actually does work and boot and do all that great stuff, right? So this isn't a theoretical exercise. So Clang really does work. Beyond that, of course, we told you yesterday that Clang is being used to build applications in Snow Leopard. So not only are we doing tests and seeing if they build, we're actually building applications, mastering them on the DVD, and shipping them to you. So when you run Automator or Interface Builder or Dashcode or Property List Editor, you're actually running Clang-compiled code, right? We're serious about this. And beyond that, we're actually building Xcode. Well, just so you have an idea of what Xcode entails, right? Xcode is not a small app. Xcode is 2 apps with 18 frameworks and 20 plugins. The source base is built out of 17 Xcode projects, and it's over 2.5 million lines of code. This is a major real-world app. This is the real deal. Now, full disclosure, about 5% of that is Objective-C++. And so this is exercising the ability of the Xcode's ability to fall back to LLVM G++ to build that, but that's still a heck of a lot of code, right? And Xcode works great, and particularly in Snow Leopard. So this is a real compiler. So for me, one of the great things about actually building applications and shipping them is not just chalk it up one, yay, compiler, you actually work. It's actually getting people to live on the compiler, right? So we've had these teams living on this compiler and doing their daily development with it. And it's really exciting to talk to these people because they have very interesting quotes. Apparently not all of them have been thrilled with GCC either. This is a great quote from Chris Espinoza. He says, "I've never seen a transition to a new compiler go as smoothly as this." And Chris adds, "When I say never, it's somewhat authoritative, having started in the garage 25 years ago." So 30 years ago. Sorry, Chris. So it's been really exciting to see people use it, and so far, from what I can tell, people seem to love it. And this is just the first of things to come, I hope. We have a lot of ideas for the future. So, to wrap things up, I want to talk briefly about the static analyzer, right? Because compilers are boring, right? We learned that yesterday. And let's talk about the new cool stuff. Well, the new cool stuff is the integration of the static analyzer with Xcode. And the Xcode team has done an amazing job of making this accessible and really useful. And so you saw a couple of demos that show you how the data flow information and the control flow information from Clang is rendered in Xcode in a way that's truly beautiful. It's really fun to use, too, if you haven't tried it yet. This works with both the Mac and the iPhone. It's easy to use opt-in stuff. If you want to learn more about this, we have a session right after this in North Beach. And the session, Ted Kremenek, the chief architect, will tell you all about it. And so it's a great session. I highly encourage you to go there. So at this point, you may be wondering, I've learned about all these different compilers. Well, which one should I actually use, right? Well, there's many different ones to choose from. So let's talk about their virtues. With Clang, building with Clang is a great option if it works for you, because you have fast compiles, you get great generated code using the LLVM optimizer in backend, and you get a great user experience. Use Clang. However, if you're using a feature that Clang doesn't support yet, like nested functions, one example, or you really care about OpenMP, then LLVM GCC is a really good answer. Now, LLVM GCC supports all the same features that GCC does, and it's not as fast as Clang when building in debug mode, but it's really fast for optimized compiles. And the LLVM optimizer is substantially faster than the GCC optimizer. You get fast generated code, and you get really good compatibility with GCC, including C++ and Objective-C++. Now, if you want the minimum possible delta from our tools release last year, GCC 4.2 is a good answer. This is the stable compiler from last year with a few bug fixes and the blocks feature. So we haven't done anything crazy. This is for people that are in the middle of their development cycle and aren't ready to switch up to a different compiler. Finally, if you're still using GCC 4.0, please stop. GCC 4.0 was a great compiler, but it's really time to move forward. And both on the Mac and the iPhone, GCC 4.2 is really the compiler you should be using at the least. And so this is the compiler landscape, and I hope that you'll have some fun with your compilers and start expecting more. So if you're interested in learning more information about compilers, you have questions, feel free to contact Michael Jurowitz. He's our developer tools evangelist.